Hi guys, in this video we'll look at the oxidation of alkenes. We have this handout here. We also have the summary page, front and back. We have, after alcohol oxidations, we can move to alkene reactions or oxidations. I'm not going to go over these here at this point, but this is a summary of what we're doing. We can refer back to this to summarize later. We also have the other handout, which is sort of a outline, oxidation of alkenes, and we'll begin with converting alkenes to cis-vicinal diols. These are also known as glycols. Okay, cis, vicinal, they're the diol, two hydroxyl groups, two OH groups. The two OH groups are next door to each other in a 1-2 position or orientation. That's called vicinal. In organic 1, we made vicinal dihalides by reacting an alkene with like Br2 or Cl2. And the two OH groups will be cis. We'll see that when we show structures. Okay. The first way to convert an alkene to a cis-vicinal diol is using potassium permanganate. Now we saw this as an oxidizing agent when oxidizing alcohols. It will also oxidize an alkene. All right. That's shown on the other handout here. Here's an example line reaction. You take cyclohexene with KMnO4, typically under basic conditions, aqueous base, hydroxide. Let's show some lone pairs there. And typically mild conditions and often cold on ice. We'll refer back to this as to why later. And here we see our diol. The OH groups are cis. Okay. Vicinal, that is a 1-2 relationship. Next door to each other. They're in the same vicinity. That's where vicinal comes from. Okay. This is also called, a diol is also known as a glycol. Now, of course, we would get an enantiomer if possible. But this is an achiral molecule, so there is no enantiomer here. Okay. Mechanism for this reaction. KMnO4 has structure like this. Okay. One anion, the potassium can sit with it, the potassium cation. And the alkene reacts with the KMnO4 in a concerted stereospecific addition. It's almost like a Diels-Alder reaction. But instead of a 2 and a 4, it's a 2 and a 3. And if we watch the movement of electrons with the 3 arrows here, these electrons move out and attack this oxygen. Okay. These electrons move on to the manganese. And these electrons move away from the manganese and move out and make bond here where those had just left. Okay. It is all concerted. That means everything happens at the same time, all the electron movement. Now if we did it stepwise and didn't include that arrow up there, when these electrons come out, we would have bond to oxygen And lone pair on manganese, that comes from these two arrows. We would have O minus, double bond here and double bond there. And this would be a plus. Yeah? Well, basically now these electrons will be attracted here. And that's going to give O Mn lone pair, double bond O, double bond O. But now this O is bonded here. One lone pair left. Oxygen has a positive charge. Manganese, actually we should come back over here. The manganese now has a negative charge. Okay, somebody correct me there, because we're net negative and somehow I went net neutral. That's wrong. We need to remain net negative. Okay. We need to remain net negative. But then to get this here, by the way, something's not shown here. This manganese has a lone pair. Okay, that's what this arrow means here, right? If my arrow is correct, and indeed it is, missing a lone pair, we see where it comes from. Now these electrons just move on to oxygen, and we get that structure there. Okay. But see, these two here, these are not actually formed. All right. All this arrow movement happens at the same time. I said concertive. It's, I don't know what that means. Concerted. Concerted. All right. There is no intermediate. Like a Diels-Alder reaction. All this happens at the same time. Boom. I just did this to sort of show you how we get there if it was sort of stepwise, but it's not. Okay. So in a concerted reaction, the alkene reacts with KMnO4, and it immediately gives this product here, which is a manganate ester. Okay, because two of the oxygens are now bonded to R groups. That's why it's called an ester. The K plus, which is here, still sits with this. All right. But this is not stable. It will break down in the presence of water. We're not going to show a mechanism for this, but basically these two bonds here will be cleaved and the oxygens will pick up H's. Really by hydrolysis. Again, we're not going to show complete mechanism, and that gives the diol. Okay. Now the fate of the manganese is actually MnO2, which is a discrete compound. Now we look at the manganese here. In KMnO4, the manganese is has an oxidation state of 7. When we're done, the manganese has an oxidation state of 4. Okay? Manganese 4. Oxygen is 2 minus, that's 4 minus, it'd be 4 plus. And so the Mn has been reduced. And if something's been reduced, something would have to have been oxidized. Well, the alkene is oxidized because we see the carbon has no bonds to a more electronegative atom. Now each carbon has a bond to a more electronegative atom. And that is one of the ways to determine that these two carbons have each been oxidized. I was trying to see the fate of the potassium here. I don't show the potassium. It can't just disappear. It's probably potassium hydroxide is formed here. But let's not worry about it, okay? We're just going to have a little magic here. We're not going to show a mechanism or a complete mechanism other than just showing that water is required here. The manganate ester is not stable. We can actually put brackets around it. It's an intermediate that's not isolated. It continues on. All right. So just a little bit of mechanistic knowledge to help us understand the reaction, a little bit of the redox considerations. Ultimately, it's a predictive product reaction. Some terminology: diols, cis-vicinal diol. Let's do an example here. Okay. Alkene. Here we have a methyl group. All right. If we had a methyl here, well, the two OH groups are going to be cis. By the way, did we note why they're cis? Because it's concerted. The KMnO4 approaches from either the top or the bottom of the alkene face. If it approaches from the top, the electrons come up, attack the manganese, and that oxygen is kind of back bonding. All right. Both bonds have to be up or down. In this case, if you show the two OHs cis going back, it's the same exact compound. But here, with the methyl group, we can show the OHs forward and cis. The methyl group would get pushed back there once this carbon becomes tetrahedral. But in this case, we would also get the enantiomer, because this is a chiral product. The enantiomer would be where both OHs, they're still cis, but they would both be back, and the methyl would be forward. Okay? In this case, an enantiomer was applicable or was possible. All right, so this reaction gives a cis-vicinal diol. How would you make a trans-vicinal diol? Is that possible? It actually is, using chemistry we've already looked at. And if we look at one OH group and consider the other one maybe a nucleophile, we have nucleophile carbon-carbon OH. Think about that. Okay. Syn or cis hydroxylation. All right. Syn is more of the term we use for a process. Okay. Concerted syn hydroxylation. Okay. We can also do this reaction using osmium tetroxide. All right. OSO4. Now the mechanism is very similar. First off, OSO4 is a neutral molecule in itself. It doesn't need a cation like MnO4. Okay? MnO4 is an anion that needs a cation to go with it. Similar structure, but it's not an anion. Similar concerted mechanism. And that gives an osmate ester. There's a lone pair there, right? Comes from that arrow right there. Now, in contrast to the permanganate ester, osmate esters are actually stable, and they can be isolated. But if you come in with some other reactant, either hydrogen peroxide or sodium bisulfite, okay, not bisulfate, but bisulfite, we can cleave the osmate ester to the cis-vicinal diol. Now again, we're not going to look at mechanism for this. Actually, one is an oxidation, one's a reduction. So it's two different mechanisms. Now this is a two-step reaction. We first make the osmate ester, then we come in with a cleavage step. Where with KMnO4, everything was together, and the cleavage happened as soon as the manganate ester was formed. Okay. Now, osmium tetroxide does give better yields for this reaction than KMnO4. But osmium tetroxide is more expensive and it's also toxic. Okay? OSO4 is actually listed as a chemical weapon. Okay? It's pretty nasty stuff. So I reckon if you're going to do this reaction, if you're looking to do this reaction, would you rather use a safer reagent that's easier to use, but maybe your yield is not as good? Or would you rather try to get a better yield by using a more expensive and perhaps quite toxic reagent? I don't know. Well, in any event, if you use osmium tetroxide, you need to be very careful with it. All right. You'll often see KMnO4 used in the undergraduate labs. I've never seen osmium tetroxide used, and I have myself never used it. Okay, now in the examples we use cyclohexene. It's easy to show the stereochemistry there, the cis, because the ring cannot rotate. What if we had a non-cyclic alkene? This, of course, is cis. We would get this product. All right. Now another way to show this outcome, which may be more helpful, and it's the way I showed in Organic 1, is to put the new groups in the plane. We know the two OH groups are vicinal, they're cis, and so if we show our alkene, if we turn it and make the two groups forward and back instead of all in the plane, we can just place our two OH groups there either straight up or straight down. All right. Now, this approach will help us when we're asked to do such reaction like this. If this alkene reacts with osmium tetroxide followed by a magic step, if you want to say, or a workup step, what's the product? Can you show the product in a Fisher projection? And then can you answer, is the product erythro or threo? Okay. And I would recommend approaching this like this. Turn the original alkene. Okay. Again, we did that some in Organic 1. So give that a try. Now we can also work backwards here. What starting material would react with the osmium tetroxide followed by the magic step to give this diol? Which, by the way, is guaifenesin, which is a common decongestant, like in Robitussin. This is pretty straightforward. I'll go ahead and just show you to illustrate an application of this reaction. take that alkene there. We can do the reaction. Either with the osmium, or we could do KMnO4. Okay, want to keep it mild though. Okay, mild and cold. If the KMnO4 is allowed to get warm, we could start cleaving this carbon-carbon bond, and we'll mention that on the next page. So with this alkene, and by the way, how would you make that alkene? You can make it from this phenol, OH and O-methyl. This is called guaiacol. Okay. Think about how you would convert guaiacol to this, and then we already showed that. That's kind of why this is called guaiphenicin, because it originally comes from guaiacol. All right. So what reagents are needed here? And then do the one at the bottom. Okay. There's also one to do in the outline page I see there. Here in the outline I show you an example of a drug that contains a cis-vicinal diol. Drug used to treat breast and colon cancer. And we can imagine how this may have been made from an alkene here. Okay, Roman numeral 2. Oxidative cleavage of cis-vicinal diols, the compounds we just made, to carbonyl compounds using periodic acid or sodium periodate. That's shown here. If you take one of these reagents, here we have periodic acid and a cis-vicinal diol, it will cleave this, okay, the carbon-carbon bond, the carbons that each have an OH group, will cleave here, and then the carbon will end up being double bonded to the oxygen. And so if this carbon double bonds to the oxygen and you have two methyls, you'll have this. And if this carbon double bonds to the oxygen, you'll have just one methyl. And the other bond this carbon is making is an H. It's there. I have drawn it in here because that functional group is an aldehyde. And seeing the H drawn in quickly lets me know that it's an aldehyde. Okay? So we cleave to two carbonyl, it doesn't say 2,2, but it does give two. Gotta be careful. If it was a ring, it wouldn't be two compounds. Gotta be careful using the word two there. In this case, it was two compounds. Down here, it's only one compound that has two carbonyl groups. Okay, mechanism. Well, it's very similar to the previous mechanisms. If we look at the structure of periodic acid, it's very similar to KMnO4, except this is protonated. It's not an anion. But this is not an alkene. Ultimately, these two OH groups react with the iodine and displace water. We're not going to show mechanism. Okay. It gives a periodate ester. This is not stable. And this will break down to two carbonyl compounds. Now look at the arrow movement here. These electrons, we can start with any arrow. Okay. These electrons come in here. Well, electrons have to leave carbon. These move up to the oxygen to make double bond there. So we just made double bond here, double bond there. And then we just broke the iodine oxygen bond over here. And then when these move up, we push the electrons off and break the other O iodine bond. Now in this electron movement, we see that this should give these two products, and the iodine should now have the OH is the same, the two double bonds to oxygen is the same, but this arrow gives it a lone pair. Here the iodine has oxidation state of +7, now it's +5, and the iodine has been reduced. This is of course unique bonding for iodine where it's oxidized. Typically halogen is one bond, 3 lone pairs, but the larger halogens can be oxidized and can sometimes have an oxidation state that's positive. And here it is as oxidized as possible at +7. It is group 7. So the iodine is reduced, something was oxidized. Well, actually the two carbons, each one was oxidized. We can see that because this carbon has one bond to an oxygen, more electronegative atom. Now the carbon has two bonds to a more electronegative atom. Same with the other carbon. Okay, ultimately it's a predict the product reaction. All right, the diol does need to be cis, otherwise the two OH groups are not going to be able to bind to that iodine if they're not on the same side. Okay, this is an example where the ring, you have a ring. Okay, what does this reaction do? It cleaves the carbon-carbon bond, and each carbon becomes double bonded to the oxygen. And that's what we have here. Now the upper carbon is going to be an aldehyde, and the lower carbon will be a ketone, because the lower carbon has a methyl group. Now if we start combining our reactions, we could take this alkene, react with osmium, followed by what is a magic step. Okay, we covered that. These two essentially give that. Okay, so what we're doing here is we're converting it. These reagents, okay, if I show them here, convert it to that. Then we can come in with the sodium periodate. By the way, when we do this, this can be an H here, or it can be an anion with a sodium cation. Okay, doesn't matter. So these three steps would give that product. I kind of consider the first and second one step. It's one transformation. It's a two-step transformation to give the diol, and then we're doing the oxidative cleavage to give the two carbonyls there. Okay, next reaction. The next reaction we're going to look at is ozonolysis using ozone, O3. All right, ozonolysis. Now, ozonolysis, you begin with an alkene, and you cleave to the two carbonyl compounds directly. That is, excuse me, it gives the same result as these three steps here, which is good news. Now, the ozonolysis, we react with ozone. It is also followed by a magic step. All right. And let's look at that reaction now. Ozonolysis is actually one of the top 10 reactions in organic chemistry. Probably. And I sometimes jokingly say there's about 20 top 10 reactions in organic chemistry. So here we're going to move to oxidative cleavage of alkenes. All right. Now we've actually already showed that. That's what we did here. By combining two previous reactions. But now let's do it directly using ozonolysis. Now this page just introduces a line reaction again, gives an example line reaction. This alkene, ozone, which is O3, all right. It's an allotrope of oxygen. Followed by either zinc metal or dimethyl sulfide. Okay. Now, first off, what does ozonolysis give in terms of just predicting products? It cleaves the carbon-carbon double bond. But it doesn't put OH groups on each carbon like osmium tetroxide, okay? Really it only cleaved the pi bond, okay? Put OH groups on each carbon. With osmium tetroxide, we cleave both the pi and the sigma bond. We completely break the two carbons apart. And each carbon becomes a carbonyl. And so if we just take it, and I'll redraw it, it's going to end up being the same thing I have there. Instead of this being double bonded to a carbon, it's going to end up being double bonded to an oxygen. And over here, we can draw this and this. And instead of this carbon being double bonded to a carbon, which, okay, we've already broke it, it ends up being double bonded to an oxygen. And if we put the lone pairs there, there are your two products, okay? But that's the same thing I have drawn here. We see one is a ketone because the original alkene had methyl groups or carbon groups on the right carbon. But the other carbonyl is an aldehyde. Let's draw in the H. Because the other carbon had one R group and the other atom on the alkene carbon was a hydrogen. It's still there. Okay, well, let's look at the mechanism. Here's ozone, a Lewis structure for ozone. I don't think you can draw a Lewis structure without any charges. Now, we could use this Lewis structure or resonance structure here, or we can do or show an alternative resonance structure where we move electrons here and we get this structure. Now, it's not as good as this structure because we lost a pi bond and we've separated the charge further. But if we work with this structure, we can more easily see how the reaction takes place. It's all concerted. We start with the pi bond. It attacks the positive oxygen. Okay. Now, if we did this sort of stepwise, we would leave a positive carbocation here. Well, that never develops because this oxygen comes in here and back bonds immediately. Okay. And this concerted mechanism gives this product here. It's called a Melozanide. It's a 5-membered ring, 3 oxygens and 2 carbons. It is not stable. It will break down. Do you see some similarities? Other things are breaking down. Peroxide ester is not stable, 5-membered ring. Okay. This will break down. This lone pair moves in to make pi bond between O and C. These electrons get pushed off and they move up here between the C and the O to make pi bond here. And when these move up, this sigma bond gets pushed onto oxygen. And this arrow movement gives these 2 molecules. There is one product. In this case, the ketone. Okay, well, all right. But the other product here is this carbonyl with an oxygen. It's called a carbonyl oxide. Net neutral. Very weird. I don't think you'll ever see a carbonyl oxide other in the ozonolysis mechanism. Now, if that was gone, it'd be your products. But it's not. And actually, these two will react back. This anion will attack this carbon. It's partial plus due to dipole here. Okay. And by the way, we'll be attacking carbonyls. Nucleophiles will be adding to carbonyls a lot during test 3 and test 4. That gives this product here. We just made this bond. If you orient yourself, I flipped the carbonyl over. Electrons up to oxygen to give 3rd lone pair to oxygen. Well, there it is. It's just flipped upside down. These electrons, this minus then attacks, we have dipole here, attacks this carbon, pushes electrons up, gives this oxygen back its 2 lone pairs. That one has 2 lone pairs. This one now has only 2 lone pairs. We get this structure here, which is a 5-membered ring. But now the 3 oxygens are no longer bonded together. With the 3 oxygens bonded together, it's not stable. This is stable. It's called an ozonide. This is called, it's MOL. Okay, if you know Spanish, I believe MAL equals bad. I think this is MOL. I consider this a bad ozonide. It rearranges through this mechanism to a good ozonide, or just ozonide. This can be isolated. Now we come in with either zinc metal or dimethyl sulfide. Okay. Both of these are reducing agents. And it works its magic. We're not going to look at this mechanism. And we end up with the 2 products we said we would get. Okay, 2 carbonyls where we just cleaved, each carbon became carbonyl. 2 oxygens remaining in the organics. That means one of the oxygen has to go somewhere the fate of the other oxygen is either zinc oxide, and we see the zinc is now 2+, it's been oxidized, or the dimethyl sulfide becomes dimethyl sulfoxide. The sulfur becomes oxidized. Now note in this reaction that aldehydes do survive. There's no reason to think they would not, at least not at this point. Okay, here's some homework. Alkenes, ozonolysis, two-step ozonolysis, okay? In this case, we have two products, and we're just saying ozonolysis. And asking here, it's a little bit vague. You could say, well, do I need to show the ozonide? No. Ozonolysis refers to, we're starting with an alkene, and we say that an alkene undergoes ozonolysis. So what alkene would you react with ozone followed by a magic step to give these two products? Thinking backwards. Okay. Now, we can also cleave alkenes using KMnO4. But wait a minute, I thought KMnO4 converted alkenes to KMnO4 converted alkenes to cis-vicinal diols. They do, if you keep it mild and cold. If you let this get too warm and hot, or if you use acid here, which makes KMnO4 a stronger oxidizing reagent, the KMnO4 will actually cleave the two carbons. The bonding between the two carbons will actually cleave this. That may even happen a little bit when you keep it mild and cold. And that may be why the yield tends to be low for getting the diol, if you don't do it under a controlled manner. Okay? Because a further oxidation is possible. Now, I'm not going to show any mechanistic thinking, but basically, an alkene, okay, this is important. If we heat and use acid, okay, this is going to be considered harsher conditions, and it will lead to cleavage of the alkene, complete cleavage, and each carbon becomes carbonyl. Just like ozonolysis, with a key exception. If you cleave your alkene with KMnO4, aldehydes will not survive. Because remember, aldehydes can be oxidized by one of the big three. All right? Remember back to oxidation of alcohols, aldehydes. If you're using one of the big three, such as KMnO4, aldehydes will be oxidized to the carboxylic acid. Okay? And so in this case, we would get this product, which is not further oxidized by KMnO4. But in this case, the aldehyde would get oxidized, okay, and we would end up with the carboxylic acid. If you do your cleavage with ozone, followed by the magic step, aldehydes will survive. Okay, and now you know why I said that here. Okay. Now, importantly, if you use reducing agents for the workup step, the magic step, there are some textbooks that show an oxidizing workup step, and in that case, aldehydes would not survive. But if you use zinc or dimethyl sulfide, they do survive, because these are not oxidizing reagents. Okay, there's a couple of homework here, a couple of miscellaneous handouts. This shows an example ozonolysis. By the way, I didn't mention it. Somewhere it says the blue color. Okay, yes. Ozone actually is blue in solution. Okay. Actually, like, you know, something like that. Maybe a little bit lighter. I don't know. Okay. You can read here some practical information. Here's the ozonolysis product. In this chemistry, they don't isolate it. They could. They don't. It then undergoes an aldol reaction to give this product. Okay. Now, we don't know that chemistry yet. It'll be covered near the end of the semester, though. Okay, the aldol reaction. But for now, this is the product you should expect upon ozonolysis of this alkene. The cyano group is not going to react in this reaction. Okay. Now, ozone is an oxidizing agent. It's going to be purged. It's a gas. It's going to be purged into the flask. It's going to come out. Okay, and we can measure or have an indication of the presence by having iodide there, and the ozone will actually oxidize iodide to iodine. Of course, you can balance that if you want. And the purple color is an indication that you have ozone. Okay, so some good practical information about how to conduct a reaction. This comes from Organic Syntheses. You can find this online. It's now free online. Okay, there is some chemistry over here where this alkene here is cleaved. All right, you can see how they do it. All right, they're actually doing two steps here, but after B, what is formed after B? Okay, kind of see if you can tell what they're doing. And then what is the C reaction? I kind of gave you some help there. This is the alkene puzzle from Organic 1. I'm giving it to you again. Of course, some of you did not have me for Organic 1. I told you in Organic 1, there's a couple of reactions that we were not covering in Organic 1, 18 and 5. And you see 18 is an ozonolysis. And then 5 is osmium tetroxide. So you can try those two reactions here. And the remainder would be some good review for a final exam. But at this point, I would just focus on 18 and 5. Okay. So we're doing some oxidation of alcohols and alkenes. Common to all these reactions, we're making carbonyl compounds. Okay, there are other applications. I'll end it there though. Here's an example of actually ozonolysis in the body. Cholesterol alkene undergoing ozonolysis in the body. Can you actually have ozone in the body? Again, an aldol reaction, which is going to be on test 4. There's a little information about it here. Okay, so there's always applications, particularly biochemical applications. Okay, guys, I'll end it there.